Welcome back. In this tutorial, we will simulate a single-phase, fully controlled bridge rectifier using MATLAB Simulink. Problem statement. Simulate a single-phase, fully controlled bridge rectifier. Observe the output voltage and current waveforms for different firing angles. Compare results with diode and semi-controlled bridge rectifiers. Before starting this tutorial, let me briefly explain how this rectifier is different from the previous one. The single-phase semi-controlled rectifier allows only unidirectional power flow, meaning energy can flow from the AC side to the DC load, but not in reverse. In contrast, the fully controlled rectifier can operate in two modes, rectification and inversion. 1. Rectification mode. The fully controlled rectifier works in the rectification mode when the firing angle is between 0 and 90 degrees. 2. Inversion mode. For the firing angle greater than 90 degrees, it is possible to obtain a negative average load voltage. In this condition, the power is fed back to the single-phase supply from the load. This operating mode is called inverter, or inverting mode, because the energy is transferred from the DC to the AC side. In practical cases, this operating mode is obtained when the load contains an active DC power source, such as a battery. So let's get started. Launch Simulink. And let's start with a previous example. Create a separate copy of the model for this session. And assign a different name. Double-click on the text and change it to fully controlled rectifier. Delete the diode blocks. Copy and paste the thyristor block twice and connect them in place of the diodes. Let's bring in Go to Blocks from the library. The Go to and from blocks are used to simplify signal routing in a Simulink model. Instead of drawing long and cluttered signal lines across the model, you can use these blocks to make the diagram cleaner and easier to understand. Since both Go to Blocks currently use the same tag, let's change the tag of one block to a different name to avoid conflicts or errors. When you hover the cursor over the output side of a Go to Block, a blue arrow will appear. You can click and drag this arrow to automatically create a from block with the same tag. To ensure proper conduction and maintain symmetry in the output waveform, each pair of diagonally opposite thyristors must be triggered with the same firing signal. Change the firing angle to 30 degrees. Go to Simulation tab and click the Run button to start the simulation. The display block is showing the DC output voltage for the firing angle of 30 degrees. The output voltage and current are delayed by 30 degrees in each cycle in both the positive and negative half cycles of the input. Next, replace the resistive load with an inductor. Set the value of inductor to 10 mH. Set the firing angle to 90 degrees. According to the equation, the average load voltage is 0, and we should obtain the same result in the simulation. Start the simulation. You can see that the value of the average output voltage is negligible. Let's examine the waveforms. The positive and negative peak values are equal in magnitude, which results in an average voltage of 0. Comparison with an uncontrolled full-wave bridge rectifier. Open the diode bridge rectifier model. Replace the resistive load with an inductor and set its value to 10 mH. Add a scope block. And connect it to the output of voltage measurement block. Connect a display block to record and monitor the average output voltage. Start the simulation. As you can see, the results are different. The fully controlled rectifier gives 0 DC voltage, while the uncontrolled rectifier produces a non-zero positive average voltage. The waveform also confirms this, as it contains no negative values. This is because, in an uncontrolled full-wave rectifier, even during the negative half cycle of the AC input, the diode switched conduction paths and redirected through the load in the positive direction. As a result, the output voltage is unidirectional and consists only of positive values. Comparison with a semi-controlled full-wave bridge rectifier. Open the previous model. Replace the resistive load with an inductor. Set the firing angle to 90 degrees. Run the simulation. You will observe that the output once again has a positive DC component. The waveform contains no negative values, which confirms that the semi-controlled rectifier maintains unidirectional current flow. Conclusion: This confirms that a fully controlled rectifier can be operated to allow bidirectional current flow, depending on the firing angle. In contrast, semi-controlled and uncontrolled rectifiers enforce unidirectional current flow. Thank you for being with us.